Last time, if you recall, we were discussing an error detector called a synchro error detector. I gave you this this schematic diagram. In this particular diagram, two devices are connected. One device is referred to as the synchro transmitter and the other device is the synchro control transformer. I told you that the two devices are identical in nature, but for the difference in their rotor construction, there is a demand on this particular rotor to be cylindrical, so that the impedance seen by this signal conditioning device should not be a function of the rotor position. Now, the requirement of this is that you see a signal which is proportional to the difference of the two shaft positions should be available to us. You keep in mind, we have already seen that how a particular potentiometer pair works. Let us say this is a potentiometer pair. This is your signal theta r, the reference. This is signal theta c, the controlled signal. If I take up this signal E, we have seen, is equal to Kp, a constant, a potentiometric constant, into theta r minus theta c. That is, it is proportional to the difference of the two shaft positions. So, exactly identical arrangement, identical equation will come with the synchro pair. The only thing is that the synchro pair is an AC device and is acting on the high frequency signals. So, in this particular case, you will find that theta r is the reference position and theta c is the controlled position, and you want to use this device as an error detector, so that the signal available here is an error signal, is a signal proportional to the difference between theta r and theta c. And this is what we are going to see as to how does it work, how do we get a signal which is proportional to the error between theta r and theta c. For that, I will like you to refer to the synchro transmitter construction, synchro transmitter working. In the case of a synchro transmitter, let me say that this is the flux pattern, and I take the transmitter in what is called the null position. So, this is theta is equal to 0, theta is being measured with respect to this position. This is synchro transmitter, this is the flux pattern. Now, since the EMF induced due to this flux pattern are being fed to the synchro control transformer, we can say that the flux pattern in the synchro control transformer will be identical. So, this is the flux pattern as far as synchro control transformer is concerned. Now, let me assume that the synchro control transformer has got this position at certain time. I want you to help me. What will be the voltage induced in the rotor of the control transformer? This is the voltage E which I am taking. I repeat my question. The synchro transmitter is in the null position and this is the flux pattern indicated. The identical flux pattern in the synchro control transformer is shown over here, and this is the position of the rotor of the synchro control transformer. I measure the angle alpha with respect to this position. So, in this particular case, please see that as far as this synchro transmitter is concerned, maximum flux is linked with this winding, and this being 90 degrees angle, so no flux is linked with this winding, and the angle, the voltage at this particular point will be 0. So, in this particular situation, when I take a rotor in this position, the voltage induced in the rotor winding of the control transformer is 0. But now you take a situation that this particular synchro transformer rotates by an angle theta and this control transmitter rotor rotates by an angle alpha. So, the net angle between the axis of the transmitter and the control transformer is 90 minus theta plus alpha, and therefore voltage induced EM, let me call it, will be equal to K dash ER cosine of 90 minus theta plus alpha into sine omega CT. This is what we have been discussing we have discussed last time, if you recall, that this becomes the factor which corresponds to the angle between the two, which corresponds to the positions of the two. When you take theta and alpha is equal to 0 with respect to the positions shown over here, you find that the voltage induced is 0. And when theta is taken with respect to the null position and alpha is taken with respect to the positions shown, in that particular case voltage induced is given by this expression. So when theta and alpha have got 90 degrees angle between the two rotors, that is theta and alpha correspond to 90 degrees angle, then the synchro pair is referred to be working in the electrical zero position. I make a statement over here, electrical zero position. In an electrical zero position, the voltage induced in the rotor winding will be 0. So it means in any position where this is theta with respect to the reference and this is alpha with respect to the reference, I have the voltage EM, I repeat this expression, K dash ER cos 90 minus theta plus alpha sine omega CT. Okay, this can be written as K dash ER sine theta minus alpha sine omega CT. Okay. Now recall the statement that the synchro pair is going to be used as an error detector in a control system. So it means as soon as the error theta minus alpha is equal to phi becomes greater than 0, the function of the controller will be to reduce this error to 0 as soon as possible. So it means once the synchro pair is taken as a part of a feedback control system, I need your attention and comment on this point. Once the synchro pair is a part of a feedback control system, the claim is this, that phi will be very small, because as soon as phi of the order of 5-7 degrees appears, the control system will act in such a way as to reduce this phi to be equal to 0. That is, the command is theta and the controlled variable is alpha. If the control system is working effectively, the controlled variable has to be equal to command signal, and therefore phi will be nearly equal to 0. Under this assumption, I can write in my model sin theta minus alpha is nearly equal to phi itself, because for small values of theta, sin theta is equal to theta in appropriate units. Okay? So if that is the case, the expression becomes EM is equal to K dash ER phi t sin omega CT. This point may please be noted, the assumption involved may be noted. You see, a highly nonlinear expression, the sinusoidal expression, has been converted into a linear expression over here under the assumption that theta minus alpha is equal to phi, a very small value, which will be true only if the synchro pair is acting as an error detector in a feedback mechanism. As an independent device, no, theta minus alpha can take any value, but if you are using this in a feedback system, naturally phi will be very small, and this approximation is valid. Okay? Now look at the input output configuration of this device. I can say that as far as this device is concerned, input is phi t, like in the case of potentiometer pair. You see, input is phi t, which is the error between the two shaft positions, the reference shaft and the feedback shaft, the reference shaft and the controlled shaft. So this is the input, and what is the output? The output is this signal EM, which is available at the rotor terminals of the control transformer. So as far as input output model of the system is concerned, I want the input output model to appear like this. This is input phi and the output is EM. Now here I need your attention, please. If I want to derive a transfer function model for this system, where input is phi and output is Em, and you will recall your Em is equal to k dash Er phi sin omega ct, the mathematical model is going to be complex. However, at this juncture I will use the information that omega c is simply a carrier which is the operational frequency of the device we are going to use. 50 cycles, 400 cycles per second, 1000 cycles per second are the typical frequencies you used. So since it is the operational frequency of the device, it really does not carry any information about the error of the system. For example, if I take this total quantity as EC, let me call it that ECT sin omega ct is Em. What is the nature of this signal? The nature of this signal, let me take a typical signal, is going to be like this. This is the output of the synchro error detector. Now look at this output. Actually the error phi is given by ECT, which is nothing but the envelope of this particular signal. So it means as far as the carrier is concerned, the carrier does not carry any information about the control action. The carrier is coming just because the device is operating at a frequency omega c. So it means as far as the mathematical model is concerned, as far as the transfer function model is concerned, I may be worried only about the carrier EC, about the envelope EC, and I should not concern myself with the total output Em, which is a modulated signal coming from the synchro error detector. And hence I can say, as far as mathematical model from the point of view of control analysis and design is concerned, the mathematical model will look like this. Phi is the input and EC is the output, where EC is the envelope of the modulated signal. And now if you see this, you can easily write the output ECS divided by the input phi s is nothing but a constant Ks, which is called the sensitivity of the synchro error detector. It is identical to the constant Kp, which you have utilized in the case of a potentiometric error detector. So this constant Ks is important to me as far as the flow of information is concerned, and this constant Ks does not depend upon the carrier frequency. Okay? So there was a little confusion last time also as to why I am interested only in the envelope and not in the total information as far as mathematical modeling is concerned. I hope this situation is now should be little more clear compared to the last lecture, that my interest is in the information flow and I am not interested in the working of the device, though I know that higher frequency will be required if I want to make my device immune to low frequency noise signals, and the selection of the carrier frequency is dependent upon this information as to what type of noise signals are going to enter the loop as far as the control system is concerned. Okay? So this is another consideration. At this juncture we are interested in the feedback loop model, and therefore my interest will be between phi and EC. So now I have a mathematical model, a simple mathematical model. The assumptions involved should be known to you. A simple mathematical model for the synchro error detector. The name synchro error detector will be given to the device consisting of a transmitter and a control transformer pair, and symbolic representation of the synchro error detector could be of this type. There is no need of showing all the windings, rotors, etc. all the time. Let me say that this is the rotor of the transmitter, the 3 stator connections here, and this is the output of the control transformer, and you can say that here I have theta r and here I show theta c. This becomes the symbolic representation, a symbol showing a synchro pair. I will be mostly using this when I take up feedback control systems. And the mathematical model, this is your Er sin omega ct you can take. This is your E at this particular point. E is equal to Ks theta r minus theta c becomes the mathematical model for my system, okay, where the carrier part has been removed. only the envelope part has been taken. Right. Now, since I have taken this as a rotating device, let me take a linear device also. Since the action is identical, I will quickly give you the mathematical model for this situation. Now, instead of a rotary motion, I have a linear motion. That motion I call it y. And this particular device has got a cylindrical form, and here I wind the primary and the secondary windings. Let me take this as the primary winding. To the primary winding I give the AC supply here of frequency omega c, that becomes the carrier. A secondary split into two parts. Let me call this as S1 and this is S2, the two secondaries, and I connect them in antiphase. And this is the output E. Now let us see how this device works. Some of you might have already come across this device. This is your LVDT, linear variable differential transformer, LVDT device. In this particular case, just see its working is simple, similar type of transformer action will be there. Let us say the core is in the central position, exact central position. The flux lines are linked to the two secondaries, and since they are in phase opposition, the net voltage E available here is 0 when they are when the core is exactly in the center position. Now take the core to the right, more flux lines are linked to S2 compared to that in S1, and therefore a voltage E of certain polarity will appear over here. Take the reverse action, the core in the opposite direction, more flux lines are linked to S1 than to S2, a voltage E will appear but will be of reverse polarity with respect to the earlier position. So it means the polarity of the voltage over here is going to give you the direction, whether the y movement is this way or that way, and the magnitude of E over here is going to give you the magnitude of the displacement. This LVDT device is a device which gives you a signal proportional to the linear motion. Synchro device, which we have considered earlier, gives you a signal which is proportional to the angular motion. So what is E? In this particular case, please see, E will be given by omega c is the carrier frequency, some constant k, ER let us say is the voltage applied to the primary winding, into YT sin omega ct. This is going to be the signal. EM, let me call it, means it is a modulated signal which will appear at this point. EM is equal to KER YT sin omega ct. The carrier part is definitely appearing over here. Same argument. Please see, as far as the information is concerned, it is carried in the envelope of this particular signal, and therefore I will be interested in the signal E is equal to Ks into Yt, where Ks is the sensitivity of this device. So the mathematical model for me as far as LVDT is concerned is again only a constant sensitivity, which you should understand is the ratio between the envelope of the output signal and the displacement y of the core. So this part should be very clear, and I am sure when I take the complete block diagram, the flow of the modulated signal and the flow of the signal, the envelope part after demodulation is carried out, will become very clear. Okay? A quick glance at the tacho generator also should be helpful at this stage. The tacho generator, what is the input, please? The input is speed, theta dot. Okay? Let me say here I have a reference winding, and ER sin omega ct I take as the input to this reference winding. The output here is again going to be a modulated signal. The output is a modulated signal, EM, which, as you know, depends upon the frequency omega c, the carrier, and the theta dot, that is the input to the particular mechanical input to the rotor. So Em, if I write the complete expression, is going to be KER omega t sin omega ct. Okay, this is your modulated signal as far as the output of the AC tacho generator is concerned. This problem was not there in the earlier case, the DC tacho generator, because the output was proportional to speed and the output was a low frequency signal, it was a DC signal. But in this case also mathematical modeling gives you the same picture, because I will be interested in the error signal E is equal to KT into omega t, where this depends only on the envelope of that signal. So demodulation is assumed to be carried out, so that you have extracted the envelope and the input output relationship is given by the envelope of the signal, of the modulated signal. Okay, I think with this we have given you all the tools necessary to take up a complete block diagram using all these types of components. But before I do this, if you don't mind, I like to review the motor case again, just giving you the final result. The motor has a reference winding, two-phase motor. I had shown a capacitor here, phase shifting capacitor. ER sin omega ct is the reference voltage. This is the voltage here. Now I need not put a modulator, I have explained it to you. The input to this system is going to be Em. Input to the control phase is going to be Em. A modulated signal may come directly or using a modulator. For example, please tell me, do you really need a modulator if a synchro error detector is feeding this particular control phase voltage? The synchro error detector, understand my question, the output of the synchro error detector, which is the output of the rotor of the synchro control transformer, if I directly connect to the control phase voltage, control phase winding over here, in that particular case no modulator is required in between, because the control phase voltage requires a modulated signal and synchro error detector is directly giving you a modulated signal. So in this case I can say that the output of the synchro error detector is directly being given to the control phase of the motor. But when you come and take up the transfer function of the motor, you could take the transfer function between the envelope of this signal and the speed of the motor or position of the motor, because the information in the system is carried into the envelope, is carried by the envelope and not by the carrier. So though the signal coming over here is directly Em, my mathematical model will concern itself with the envelope and the speed, and this relation we have already derived. Let me take omega as the speed, theta as the position, and here I take the load as J and B, and I had taken Tm as the disturbance, Tw as the disturbance, Tm is the torque over here. Okay. Now please see, I think I can use exactly the same slide which I used last time. This was the mathematical model we had derived using the torque speed characteristics. Tm, recall the equation please, Tm is equal to K1 EC minus K2 theta dot. EC is the envelope of the input to the control phase voltage, minus K2 theta dot is equal to J theta double dot plus B theta dot plus Tw. Please see, EC is the input, K1 EC coming over here. I put a block over here, and from this I will give you a signal K2 theta dot. What is the advantage of this representation? The advantage of this representation is this, that now the torque produced by the motor is available as a variable. See this little change I am making in the block diagram I have given you earlier. Though the two block diagrams are identical as far as input output information is concerned, but this block diagram gives you the torque produced by the motor as a variable in the system. So Tm you can see is given by K1 into EC minus k2 into theta dot. So it means this should come from the omega, from speed, and that this particular block diagram I will complete. Help me please, what should I do next? If you are getting me, please help me. What should I do next? How do I complete this block diagram? Tm is available. Tm is the torque produced by the motor. I can now take up the disturbance torque here. This is plus, this is minus, this is Tw. So that now this is the net torque available to drive the load. And the load is given by 1 over Js plus B. So this gives me omega. Please see now, from here I pick up omega and it is the feedback loop. Inherent feedback loop in the system. You have not connected any device to give this feedback. This is an inherent feedback loop in the system, identical to the situation we had in an armature controlled DC motor. So this omega, if you are interested in theta, you can put 1 over S over here and a transfer function between theta and EC, or a transfer function between theta and Tw is available. I make a statement that this particular block diagram is more complete in the sense it gives you information about the torque produced by the motor, and it brings out the inherent feedback nature of the system. Okay, and we will be mostly using this particular block diagram whenever an AC motor is taken as a component in a feedback system. Okay, fine. I think we are ready with the tools. The tools have been completed, and I can take a practical situation now. The practical system I take, and you will help me to draw the block diagram of this system. The system is a heavy telephoto camera is there, and I want to use a motor, an AC motor, to control the position of the telephoto camera. Okay, this is the requirement, this is the control problem. I repeat the control problem. The load is a telephoto camera, a heavy load, which you want to control with the help of the devices we have considered today and in the last lecture, that is an AC motor, a synchro error detector, and other devices if required. So what I do is I first consider well, sorry, the diagram has not come nicely, but doesn't matter, this explains the situation. This is the camera, and naturally I will require large torques to rotate it, and for that I am going to use a gear train, because large torques will be required for its rotation, and a motor cannot produce that much of torque. A suitable gear train will be required. So this is the gear train, and this particular gear, the primary gear, has teeth N1, the secondary gear has teeth N2. As is seen, this will result into torque magnification and speed reduction. So this particular gear, naturally the motor is going to produce the torque and drive this particular gear, and if I am going to use an AC motor, the schematic will look like this. AC motor is driving this, and the torque produced is Tm, and the position is theta m. Here let me say the position is theta L, and let me say that there is a disturbance on the system, and this disturbance could be taken as Tw. Tw is the disturbance. Okay. Now this particular motor will have two windings. One will be a reference winding, so let me have a reference winding and a phase shifting capacitor over here. The control phase winding is going to have the voltage Em, which is the modulated signal. This particular modulated signal should be proportional to the error between the commanded position and the actual position. The actual position of the camera is given by theta L. Now you require a commanded position. How do we give the command? Let me say that to this particular signal I give the command this way. theta r this is your ER sine omega CT coming over here. A synchro pair here. Yes. You see that this is my spotting scope. This is the spotting scope, and the spotting scope is the command signal as well. Because if you have spotted a particular scene which you want to capture, a particular situation which you want to capture in your camera, you will like that your camera should follow the command over here. So this spotting scope is the movement of this spotting scope is the command signal, and this is the control signal. You want that theta r minus theta L should be reflected as far as this voltage input is concerned. Tell me please, how do I connect this synchro pair? Just see, this is your reference signal of the synchro transmitter. This is my synchro transmitter device, and this is synchro control transformer. So though it has not nicely come under this particular diagram, but I think it will become clear if I connect this. So this particular gear is mechanically connected to this rotor, so that the input to this particular synchro pair is theta r minus theta L. I hope this is clear. As far as this synchro pair is concerned, the transmitter is rotating. The transmitter movement is given by theta r, and the control transformer rotor movement is given by theta L, a suitable mechanical link. So it means this particular signal is a modulated signal, omega c being the modulation frequency, and the envelope is proportional to the error between theta r and theta L. Now this is an intelligence signal. This particular signal may not have the required power to drive the AC motor. So what do you require? You simply require a suitable amplifier, an AC amplifier between this input and this output. So let me say that between these two devices, between these two signals, I connect an amplifier of amplification Ka. So naturally this becomes the total block diagram, the total schematic diagram, though it has not come nicely, but I think the functioning of the system is more or less clear. So see the nature of the signals in this particular case. Nowhere demodulation or modulation is required, because the signals are of the nature that the devices are compatible. In this particular case, theta r minus theta c is a DC device, DC signal. Theta r minus theta L is a DC signal, and the output of this synchro device is a modulated signal. So as such, your synchro device, if you see the basic definition of a modulating device, your synchro device is acting as a modulator, because it is accepting a DC signal which is theta r minus theta L and is giving out a modulated signal whose frequency is given by omega c. Now this modulated signal is being amplified by an AC amplifier, and the output is a modulated signal again here. The frequency in the reference here also should be same as that omega c for the two devices to be compatible. So this modulated signal is being fed to the control phase, and this control motor is producing a torque and hence a position theta m, which is again a DC signal. Can I say that in this particular case your AC motor is acting as a demodulator? So it means actually the two devices are compatible. One is acting as a modulator, the other as a demodulator. So the input here is a DC signal, the output of the total device is a DC signal, the total system is functioning on the DC information signals, and hence in between modulation or demodulation devices are not required. Okay. So now in this particular case, if I want a mathematical model of this particular system, the carrier frequency part I will simply remove. If I remove the carrier frequency part and I want to write the mathematical model of the system, you will help me. I will first get the block diagram and reduce that block diagram into a suitable transfer function model. So I get started with the command signal. Yes, this is theta r. It is being compared with the actual signal, actual control signal, which you know is theta L. So you please speak out. What should I put over here? So that here is the input signal, that is, here is the error signal produced by the synchro error detector. At this particular point, yes, Ks, the sensitivity of the synchro error detector. Okay, so here I have the output of the synchro error detector, the envelope of it only. Now this is going to the motor, no, amplifier. So this is Ka. So here is an amplified signal which is being fed to the control phase of the servo motor. Now I will like to take up the transfer function model or the block diagram model of the servo motor. Recall the block diagram. I have K1 over here, a constant of the servo motor. This K1, this gives me a K1 into EC signal. This I can take as EC variable, the envelope of the input to the control phase. So this is plus and here it is minus. Yes, here I have the torque produced by the motor. I have the error signal here, the disturbance signal here. Help me, what should I write here? The disturbance signal at this particular point. I need your help, please. Is it TW? Think about it. I proceed further. So this is the net signal which is coming. NTW. Please see, it is NTW because the disturbance reflected on the motor is NTW, where N is the gear ratio. TW is not directly acting on the motor now. It is through the gear set, and therefore the disturbance is NTW. So this is the net torque available to drive the load, and the load parameters of the camera are JL and BL. Let me say, when they are reflected onto the motor, let us say they become J and B, therefore I am writing 1 over JS plus B. The parameters of the camera, the telephoto camera, are different. They are JL and BL. The values J and B are the values, equivalent values, when those values, the JL and BL, have been reflected onto the motor shaft, and the inertia and friction of the motor shaft also has been added to those values. So I get this as the effective model on the motor shaft. This gives me omega. Oh, this here I put 1 over S over here block. This gives me theta. From omega I pick up this particular feedback signal which is inherent in the motor. The constant is K2. This completes the block diagram model of the motor. The only point of caution is this, that the NTW is the reflected torque on the motor and J and B are the equivalent quantities on the motor shaft. Now this theta m, this theta m has to be converted into theta L. So let me put a gear ratio N over here. This becomes theta L. Well, the management of the slide is to be done properly so that it is visible to you. Yes, I hope this is okay now. This is theta m, the motor shaft position. I am putting a gear ratio N over here. This is theta L, the load shaft position, and to the synchro error detector, it is the load shaft position which is being fed back, and therefore I connect this and take it to the error detector and complete the block diagram. The block diagram now should be seen in this way, wherein the output is theta L, the position of the telephoto camera, and the input is theta R, which is the position of the spotting scope. So what you require is, when you move the spotting scope, the telephoto camera should automatically move without any transients. You have to suppress the transients so that it should not oscillate, and you should suppress this accuracy. At the steady state, the accuracy should be as you want. that is theta r should be equal to theta l, the steady state error should be reduced to 0. This is what you want, and this is what is the control design problem. And when we come to design, you will see that this pure amplifier, which is nothing but only a proportional control, will be replaced by a more sophisticated controller which may have some proportional action, integral action, derivative action, or some other action. Please, this point may please be noted. At this juncture, the interest is only to give you the hardware familiarity. The control problem is still ahead of us. We have to define the control problem and solve the control design problem. The control design problem will be of this nature. Please get the feel of it. That I want theta L to follow theta R under suitable performance specifications. The performance specifications will be of the nature that under steady state condition, theta r should be equal to theta r, or theta l should be equal to theta r exactly with no error, and theta l should approach theta r with minimum of transients. And to achieve this objective, I will replace this block by a more complicated block, and that particular block will be referred to as a controller, and the objective will be to design that controller. And three basic actions of the controller have already been hinted at. The three basic actions are the proportional action, the integral action, and the derivative action. Well, these are only the guidelines. The controller actions which are more complex than these actions are also allowed. Okay? This will be your control problem, as we will see. Yes, one more situation. You have helped me in this particular situation. One more feedback situation, and again I expect, well, I think, let me create suitable space, and therefore I take a gear train this way. I have a gear set. On this side I have a load, and let us say that the parameters of the load are J, L and BL, and the torque on the disturbance torque is TW, and the position is theta L as far as the load is concerned. Now I have two restrictions, please. You have to give me a suitable system configuration, and then we shall convert that configuration into a block diagram. I want to drive this load. The restriction I have is this, that I want to use a DC motor and not an AC motor as an actuator. You know that DC motor is a linear device. The torque speed characteristics of the DC motor are linear as opposed to AC motor. And the torque handling capability of a DC motor is more than that of an AC motor for an equivalent size. So I want to go for an DC motor as an actuator. So it means, as far as this primary gear is concerned, this primary gear is connected to a DC motor. So this is the armature voltage EA, which is the controlling signal. This is one constraint. Another constraint is this, that instead of a potentiometric error detector, I want to use a synchro error detector. The reason? Potentiometric error detector has got the resolution problem. It has got a better resolution, the synchro error detector, and it has a better linearity property. It has better ruggedness compared to the potentiometric error detector. Since the contact problem is there in potentiometric error detector, synchro error detector is normally preferred over the potentiometric one. So with that in mind, I want to settle for a potentiometric, a synchro error detector for this system. So for that, you please see, the load will be connected to the rotor of the synchro transmitter. This is your reference voltage. This is the rotor of the synchro transmitter, and here is a synchro control transformer. Sorry, I take this as the output at this particular point, and the shaft of this will now be connected to this reference will come to the, I mean, could you get the type of error? I am making an error I will correct this error, but let me see whether you have got the error or not. What is the type of error? Yes. Please see, what I have done is, this particular gear, which is the controlled position, should be connected to the control transformer and not to the transmitter. This is the error I have made, and therefore let me redraw this diagram. Motor connection is all right. Motor is all right. This is your load, okay, JLBL, and here I take theta L. This is the disturbance. Now this is the shaft over here. The reference in this particular case, let me take a synchro control transformer pair like this. This load should be connected here, and here is your reference supply, and here is your reference input theta r. The synchro transmitter will have the reference input, the command signal, and the synchro control transformer will have the controlled shaft connected to it. So this is the controlled shaft I have connected to it. Now where is the output? The output in this particular case is available here. Let me say that this is the output from the synchro control transformer. Now I need your help, please. What should I do if I want to interface this particular signal to the DC motor after appropriate amplification? I need suggestions from you. After appropriate amplification, this particular signal has to be connected to the armature of the DC motor. I had two constraints. I wanted to use DC motor as an actuator, and I wanted to use synchro pair as an error detector. Suggestions, please? Okay, fine. The answer has turned out to be too simple. So let me make it a little more complicated. My question, I want to make a complicated question, more complex. What I want to do is, this particular signal I want that is to go to a controller, and the controller is a PD controller, proportional derivative. It is a PD controller, that is, I want to generate a signal which is proportional to this signal, and a component is proportional to the derivative of this signal. A PD controller is to come in between. So what do you suggest in this case? Can I use op-amp directly here? Suggestion is op-amp. Okay, PD circuit I want to use. And where is the PD circuit? Let me use make an appropriate PD circuit. R1 C. I am making minus plus. Okay, this is a PD circuit, R2 over here. This you can verify very easily that it gives you a signal which is proportional to the error and proportional to the derivative of the error, where E error is the input over here. It is a PD circuit. Now my question to you is, can I connect this as an input here? We want an envelope detector. Why? We want to follow that. This point may please be noted that the PD action, the proportional derivative action which you want to take, this is on the information which is there as far as this particular system is concerned, the information about the error. You will not like to take the derivative of the carrier and feed it to the motor. This point may please be noted. You will not like to take the derivative of the carrier. You will like to take the derivative of the envelope only, because envelope is the information signal which gives you the information about the error between theta r and theta l. So you definitely require, in this particular case, if a PD circuit, if suppose you rather did not use a PD circuit over here, an AC amplifier could have been taken, and after the AC amplifier a rectification could have given you a DC signal. Please see, if derivative action was not required, an AC amplifier over here followed by a rectifier was a suitable system configuration. But if derivative action is required, the derivative has to be taken on the information signal. So it is necessary that you first extract that envelope, and for that you will require a demodulator here. So that the envelope is extracted, this particular envelope now is the input to this particular PD circuit, so that the output at this particular point is proportional to the signal E and the derivative of this signal. I leave this as an exercise to you, that here if I have a amplifier Ka, this is an EA, this is an amplifier with amplification Ka, this gives the complete block diagram to the system. However, one point I am leaving pending to you, that as far as this particular portion is concerned, when you take up the transfer function of this, a negative sign will be introduced. Okay? So please take care of this. Take a suitable inverting amplifier over here to take care of that negative sign. You will see, you write the transfer function of this, a negative sign will be introduced. Use an inverting amplifier at this particular point of transfer function 1. So in that particular case, the negative sign will be annulled, and you will be able to get the total transfer, the positive constant over here, positive transfer function over here. Last point, how about the transfer function of the demodulator, please? You said that you are using a demodulator between this signal and E, and if you write a block diagram for this particular system, you will require a demodulator transfer function. Help me, what should be the transfer function of the demodulator? Could we take it as a unity? If you assume ideal conditions, that input to this actually is a modulated signal, but you have been taking only the envelope, the output is the envelope, so envelope you have extracted, so the transfer function between the envelope of the modulated signal here and the output of the demodulator is equal to 1. So if you assume the demodulator as an ideal operation, in that particular case the transfer function of the demodulator could be taken as unity. So just 1 minute, theta r is your command signal, theta L is coming from here, Ks, this is the output from the synchro error detector. Demodulator gives you 1, so there is no need of this. This I am writing as Kc into 1 plus Tds as the transfer function of a PD controller, which you can get in terms of resistance and capacitance values given to you, and assuming that a suitable inverting amplifier you have already introduced. Here I have an amplifier Ka, this gives you the signal Ea. Use a motor here, this gives you the signal theta m, gear ratio n, this gives you the signal n, and this is fed back, this is the complete block diagram. The motor I am using as a block, the complete block diagram of the motor is already known to you. Thank you.